Compiler construction class 3. So what we did previously is we defined the R0 language. Then after defining the R0 language, we made a few metaprograms on it. We made an interpret function, which took R0 and gave us an answer. We made the optimize function, which took R0 to R0. Then what we did is we defined the X0 language, and we wrote an interpreter for it, which I'll write interp x, and this one R, which takes an X0 program and gives an answer. We also made the R1 language, and we updated these things. Okay, now, these two languages, R1 and X0, basically define like two endpoints of what we're going to be doing. We need to be able to define programs that are worth evaluating. You know what I mean? You might like Java or JavaScript or something like that, and so that's really what R is. Now, X, on the other hand, it represents x86 assembler, and it's what our actual machine can really run. Okay, so because that's what our machine can really run, the job of our compiler is to take R1 programs and produce X0 programs. So ultimately, compile is going to take an R1 program and produce an X0 program. And inside of this compiler, we have to deal with all of the differences between these languages. So what do I mean by these differences? So like R1, how can we define this language? Well, its expressions are tree-shaped, and they have this recursive expression-oriented structure. Because you can write computations like +1, +2, minus, +3, 4. Okay, so there's this deep tree of expressions. Similarly, it has an infinite number of variables because we can use let as many times as we want. Okay. Finally, variables are scoped. Now what I mean by scoped is that we can have an addition where on one side there's a let x, and on the other side there's a let x. And these two x's don't conflict with one another. We don't mix up one for the other. Now in contrast, the X0 language, it is linear because we just have a sequence of instructions. Similarly, it's heavily structured. Now what I mean by structured? What I mean by heavily structured is that we have the program, and then inside of program are blocks. And inside of blocks, there are instructions. Then inside of instructions, there are arguments. And inside of an instruction is never another instruction, and inside of a block is never another block. There's this like separation between everything. In contrast with the R1 language, expressions can go anywhere. Similarly, another thing that's different about it is that it has a fixed number/set of registers. So rather than having an infinite number of variables, there's just a very small number of them, and registers and memory are global. So there are big differences between these two languages. And so basically the job of our compiler will be to take all the things that are different about the R1 language and slowly get rid of them. So for instance, we're going to have to get rid of the fact that variables are scoped. We're going to have to get rid of the fact that there are infinite variables. We're going to have to get rid of the tree-shaped, recursive, and uniform structure. We have to get rid of each one of those things. Now, when you think about doing an analysis on a program, there's basically sort of like different ways of thinking about how that analysis works. So if you think of our program as being a tree, so I'm going to draw a tree right here. Okay, so this right here represents our program. Sometimes we can, so this is like an R1 program. And what we ultimately want to do is we ultimately want to transform it into a X0 program. this represents one block, this represents another block, and the sequence of them represent the instructions, and then maybe inside of each instruction are the arguments, which I'll write as triangles. Okay, so there's this very concrete structure here. Now, one way that you can think about compiling is to do compilation entirely locally. And what local means is that you have one node in our tree over here, and we can transform that into a particular sequence of instructions. So an example of this might be the negation operation. You might imagine being able to go through your program and just replace each negation with something. Now, unfortunately, there are basically no local ways that we can locally transform an R1 program into an X0 program. And basically the reason why has to do with the fact that the registers are global and that there's this fixed set of registers. So because of that, we don't really know where to store anything inside of the X0 program. Other transformations can be top-down. What top-down means, that means that we learn information. So I'm going to represent information as a box. So we start off with very little information, and then as we go down the program, we get more information until we have so much information that now we can transform things. So one way to think about this might be that, imagine at the start of the program, we say that there are 0 variables, and as we work down the program, we learn that there are more and more and more variables, and then we assign where those variables live inside of registers based on information that we learned before. Another way is bottom up. Bottom up. And with bottom up, we start off with information in a small amount on the leaves. Then as we go up, we learn more information until we ultimately reach the top of the program and we have all the information that we need. So an example of this might be another way of looking at variables, where maybe what we want to do is we want to look at the leaves of the program and figure out how many times variables are looked at. And then as we go up the program, we can then see, aha, this one's looked at here and it's looked at more, and gradually combine all the information until we get to the top, and we now know how many times a variable has been looked at. Finally, there are fixed point or cyclic information. Cyclic. Now, cyclic information basically means that information that we need at the top depends on information that we need at the bottom. So we need to go down and get information, and then come back up and get information, which then influences how we take information down, which influences how we give information back. And we keep doing this until every time we go down and back, we don't get it until when we go one round trip, we don't learn anything more than we did before. So these are the 4 different ways of structuring programs that look at trees in general. And of course, since programs, their data structures are trees, this represents the different ways that you can write programs. Basically, what is going to happen is that we're not going to directly go from R0 to X0. Instead, what we're going to do is we're going to make a whole bunch of little tiny programs. And each one of these little tiny programs will be one of these styles. It'll either be a top-down program, or a bottom-up program, or a local program, or a fixed-point program. And each one of them is going to remove one tiny piece of what makes R, and make it so it eventually becomes X. This is called compilation with intermediate languages. Intermediate languages. And it is the most common way to do modern compiler design. What we're going to do is I'm going to draw a picture of what the structure we're going to use is, and then over the next little bit we'll talk about actually how to do each one of these things. All right. So the first thing that we're going to do so we start off with R1. We're going to do something that is going to produce another R1 program, and this is going to be called Uniquify. The job of Uniquify is to remove scope. Now what we mean by remove scope is that what Uniquify is going to do is it's going to look at the program and it's going to say, well, there's an x in this part of the program and another x in that part of the program. So I'm going to change this one to x0 and this one over here to x1. Or there's a y over here and a y down there, and so this one will be y0 and that one will be y1. So it'll make it so that all the different variables all become totally unique, and thus they can be global. Next, what we'll do is we'll run a program that's going to be called Flatten. Flatten. And it is going to produce an intermediate language that we're going to call C0. And what it's going to do is it's going to remove nesting. So remember, the R1 language is a language that has this sort of like uniform structure where there's an expression, and inside of expressions are more expressions. And what the C0 language is going to do is it's going to get rid of that. It's still going to have variables and things like that, but all the variables are going to be global because we've removed scope with Uniquify. And then this is going to remove that remove that uniformity. Then what we're going to do, and by the way, this is going to be a top-down transformation. This is going to be basically a bottom-up transformation. And then we're going to go to x0 and a step called select instructions. And what select instructions is going to do is it's going to do a local transformation. Locally replace with instructions. So it's going to take the broad structure that C0 has and turn it into the x0 style. Then what we're going to do is we're going to do an operation that's going to be called assign homes. And it is going to be a cyclic operation that is going to remove infinite variables. And then we're going to do another operation that's going to be called patch. And this one is going to be a local thing that's going to fix x86 weirdness, we'll just call it. Basically, these passes are going to assume that x86 can do things that it really can't, and then we're going to fix it up there. Now, this code is going to be the code that we ultimately run. And this entire arrow right here, that's what our compiler is. Our compiler takes an R1 program and produces an x0 program by going through all these intermediate steps right here. All right. So that's what kind of our game plan is, and we're going to slowly unravel this over the next few classes. All right. So let's first define what this C0 thing is, so you even know what that intermediate spot is. C0 is going to be very similar to the x0 language. It's sort of a mixture of x0 and R. So it looks like this. So C0 has programs, which we write as program, and then some info, and then a mapping from a label to a tail. And there's many of these. Now what a tail is it either is a return of an argument, or it is a sequence of a statement and a tail. What a statement is a mutation, that's set, of a variable to an expression. An expression is either an argument, or a call to read, or a negation of an argument, or an addition of two arguments. And an argument is either a number or a variable. All right, now notice that this language right here is simpler than the X language because it has variables, it doesn't have registers. When I say simpler, what I mean is more easy to use, so it's more expressive. But it's more complicated / harder to use / more basic than the R language because it has these structured labels and it has this structuring right here where you can't have intermediate forms. All right, so this is what the C0 language is. Now let's write an interpreter for C0 so that we can make sure that we understand what it does. Okay, so we're going to write a function that's called interp_c. And so let's call it CI for C interpreter. So we'll write CIP, which is going to take a program and produce an answer. All right, and what it's going to do is CIP of a program with some info that we don't care about, and a label to tail map. It is going to be it's going to equal CIT, that's going to be the C interpreter for a tail, of an empty environment, which we'll write as the empty set, and then calling label to tail map of main. So we're going to look at what the main label is. Okay, and that means we're going to look up inside of this mapping from label to tail, and we're going to find the one that's labeled main. All right, now CIT, it is going to take a tail and an environment. So it'll have the environment, and then we have to look at each one of the tails. So if it gets called with return of an argument, then this will return the CIA, that's C interpreter for an argument, environment, and the arg. And if instead it were called with a sequence of a statement and a tail, we're going to get CIT of a new environment, and this new environment is going to be the result of calling CIE for expression. All right, sorry, not that. CIS for statement. CIS of the old environment and the statement, and then the new tail T. All right. 3.5. Now CIS is going to take a statement, and there's only one kind of statement, so it gets an environment and a set of some variable in some expression. And what it's going to equal is it's going to equal the old environment with the new mapping that goes from the variable to CIE of the environment NE. Now what's CIE? Well, CIE, it takes an environment and then an expression. And so what the various expressions could be is they could be an argument A. And if it's an argument, then it'll just return CIA of the environment and the argument. It could instead be a read, in which case we'll read from the user. The exact same way that we read in R0, R1, X0, and so on. It could be a negation of some argument, in which case we'll have -1 times CIA of the environment and the argument, or it could be an addition of a left and a right, in which case we'll do CIA of the left plus CIA of the right. Finally, we need to say how the CIA function works. So CIA on an environment and a number n will just equal that number. And if instead we have a variable v, then what we'll do is we'll look up in the environment what the value of the variable is. So what this does is we have now defined the C0 language. And the C0 language has a very simple interpreter. All it does is we start off in the main label. We go through each instruction until we get to a return. And once we see the return, then we're done with whatever that argument is. And as we see statements, they update the environment by assigning variables to new values based on what the previous variables were. Okay, so this is what the C0 language is. So now what we need to do is start going through and defining each one of these functions. When I say these functions, I mean these functions. Uniquify, flatten, select instructions, assign homes, patch. By the way, this flatten one, I actually call it RCO for remove complex. That's the way that I call it in the project notes. So sorry about using two different words. All right. So let's start with the first one. So the first one is called Uniquify, and it takes an R1 program and returns an R1 program. And its job is to remove scopedness from R. For example, imagine that we had the program plus let x equals 7 in x and let x equal 8 in let x equal 1 plus x in plus xx. Close the plus, close the first let, close the second let, close the plus. So this right here is a valid program, and notice that it defines 3 different x's. This one, and this one. So after the Uniquify step, we're going to turn this into the following program. It's going to be turned into plus of let variable 0 equals 7 in variable 0. Then it'll say let variable 1 equals 8 inside of let variable 2 equals 1 plus variable 1 in plus variable 2, variable 2. So notice that we have removed the names from the old variables, the names that were in the original program, and replaced them with basically like a counter. And this counter has made it so that every variable is now completely unique. All right? The way that Uniquify works, we'll call it uni. Uni is going to be a function that takes a mapping from an old name of a variable to a new name of a variable, and it takes the expression, and then it returns a new expression. We call this mapping row. The reason we call it row is because row starts with an R, and this is a renaming. So it's a renaming, so we call it row. So the definition of uni is very simple. So uni of row and a variable v is equal to just calling row on that variable v, because it's going to look it up and figure out what the new thing is. Technically, I suppose that we should write this a little bit differently. We should write erase that. We should say that it's a new variable where the variable itself is row v. Now, if we call uni on a let, where you have let x, xe, be, all right, then what is this going to be? Well, it's going to equal let x prime, and then we're going to call uni on row of xe, and we're going to call uni on row prime of be, where x prime is the next variable, and row prime is equal to the original row with a mapping from x to x prime. All right, now when I say the next variable, what I mean is that this uni function has to have access to some counter that's going to keep track of how many variables there's been. And these have to be totally unique. So it can't be part of row. It has to be like a global variable, let's say. Now, these two are the most interesting cases. All the other cases are just a, what's the right way to say this? A like a transparent mapping over the rest of the structure. So what I mean by that is that if we take like uni row of add left and right, then it just equals an add where we have uni row of left and uni row of right. And if we call it on the negation of some expression, then we get the negation of the uni row of that expression. And if we call it on a number, then we just get back that number. Okay, so these cases of Uniquify are boring. So the other ones they're the interesting ones. All right, so Uniquify is a very simple function. Now, every time you write functions, you should always test them. Now, we have a very easy way to test programs, because what you can do is you can write something like this. You can write something like, so remember, you have in your program, you have for all, sorry, it's not, that's not the way that I wrote it before. In your program, you have something like for I equals 0 to 1024, P equals a random program that's like 6 deep or something like that. And then one of the things that you do is you say check that calling interp on P is equal to calling interp on optimize of P. All right? Well, what you can do is you can add another step where what you can do is instead you can say, let's check that calling interp on P is equal to calling interp on uni of P. And in fact, you don't really care about this anymore because you just care if these things are all equal. So what I did is I wrote a little function that's called check all equal. And what it does is you give it the first program, P, and then you give it the second program, uni of P, and then you give it the third program, which is the optimization of uni of P. And then what it's going to do is it's going to interpret this one, make sure it's the same as interpreting that one, which makes sure it's the same as interpreting that one. And you may want to like name this uni P to be something so you don't have to call the algorithm multiple times. But basically, you now, because you have the interpreter and you know that these programs that look at, these programs that analyze R programs are not supposed to change its meaning. That then allows you to make sure that every single intermediate step of this diagram right here never changes the meaning of interp. You call interp on R1, then you uniquify. You call interp on that, you make sure they're the same. Then you call flatten, you call interp on that and make sure they're the same. Then you call select, call interp on that, make sure they're the same, and so on. Actually, and kind of there's another step, which is that we have opt right here. Right, so we have R1, optimize it to R1, then we unique, flatten, select, assign, patch, then we go. And if we call interp on every single step and make sure the answers are the same, and we did this on random programs, then we'll now know that our compiler works correctly. Okay, so that was Uniquify. The next program that we want to define is the Flatten Program. Or we'll call it RCO for remove complex or remove recursive structure. And we're on 3.8. Okay, 3.8. So we'll call it RCO, and it takes an R1 program and returns a C0 program. And we're going to assume that all variables are unique. You'll literally be able to run this program on any R1 program, but it's only guaranteed to work if it's called on a C0 program. Actually, Yeah, okay, sorry. You know what? It's not, it's gonna return an R1 program. We'll call it an R1 star program. Okay. But really what we're gonna do is we're gonna make Flatten. It's gonna be two separate programs. It's gonna be one that's called exploitate control, and then it's gonna compose that with RCO. RCO is going to take an R1 program and return another R1 program, but it's going to be one that is guaranteed to have the same structure that C0 wants. So here's what I mean by that. The output of RCO is going to look like this. You're going to have a program, and it'll be, program info, and then there's going to be an E. And then an E is either going to be an arg or a let of an x equals c inside of E, and a C is either going to be a read, a call to read, or it's going to be a negation of an arg, or it's going to be an addition of two args. And then an arg is going to be a number or a variable. Now notice that this is still literally an R1 program, but it's just a subset of R1 programs. All right. So for example, suppose our input to this were something like this, where we said add of plus 2, 3, and then we had let x equals read in x plus x. Okay, so suppose that we got that program. Well, the output of this program is going to be the following. It's going to say let v0 equal plus 2, 3 in let x equals read in let v1 equals x plus x in let v2 equal v0 plus v1 in v2. Close the bottom let, next let, next let, next let, next let. So this right here is going to be the output of this program. Now notice that what we did is we took this addition of this 2, 3 and we lifted it up and we made it a variable. Then we had this let x equal something and we made it a variable. Then we have the plus xx, we made that a variable v1. Then we made the addition right there into a variable v2, and then that's what we returned. All right. Now let's define the RCO function. So RCO is going to take a mapping from variables, some variables to expressions, and it's going to take an expression, and then what it's going to do is it's going to return two things. It's going to return a list of a variable and an expression, and it's going to return an expression. And this expression right here is guaranteed to be an arg. This expression is guaranteed to be a c. This expression right here is guaranteed to be an arg. And this expression can be anything. All right. So if we call RCO on a program I with some expression E, then what we're going to do is we're going to call RCO on an empty one of these mappings. Sorry. We're going to, right. we're going to call RCO on an empty one of these mappings, because we don't know anything yet, and that expression E. And that is going to return, let me put it on this side. Well, yeah, I need a little bit more space. Let's move it over here. All right. All right. That's going to return an arg, that's this arg. Then it's going to return a list of variables. Those variables, so we're going to have x0, c0, dot, 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 xn, cn. Okay? And so what we're going to return is we're going to return let of x0 equals c0 in let, sorry, and then there's going to be a whole bunch of those, and then let of xn equals cn in answer. So basically what goes on is that when you call RCO, you get back a list of all the variables that you're going to need combined with their complex expression, and then the final answer that you want. All right, now how is this going to work? So when we call RCO and we give it, we're going to call this thing row also because it's a renaming of this variable for some argument. If you give it a number, n, then we'll return a pair of an empty list and just the number n. If you instead were to give it a variable, x, then we're going to return an empty list, and then we're going to look up inside of row what x is. Now what if we have a plus? We have plus of e left and e right. This is going to be the most interesting case. Here's what we're going to do. We're going to return a pair of the new variables from the left appended with the new variables from the right appended with a list that maps x to the addition. This right here is really an add node, right? The addition of the argument for the left and the argument for the right. And then we're going to return as our argument x. Now what are these things? Where the new variables for the left and add left is what happens when you call RCO on row and the expression on the left. And the new variables on the right and arg right is what you get when you call RCO on row and the arguments on the right. And then x is a fresh variable. Right? Now, I feel like I've been switching pages a lot, but I really want this algorithm to be on one page if possible. So what I'm going to do is I'm going to move the camera down and see if that is a good way to do this. All right. Okay. All right. Now, what about when we call RCO row on a negation of some expression on the left, let's call it? Well, in that case, we'll have the new variables on the left combined with x is a negation of the argument on the left, and then x, where the new variables on the left and the argument on the left is equal to RCO of sigma and the expression on the left. So we're almost done. We next need RCO when we're called with a read. In this case, we just return a list that has x and a read. close that, and x. Okay, so we have number, variable, add, negation, read. All that's left is for a let. This is probably the most interesting case. So we have RCO sigma, rho, and we have let of x, xe, and the body expression. And now all of the exciting action is going to happen right here. Here's what we're going to do. We're going to return the new variables for the x and the new variables for the body. And then we're going to return the argument for the body. All right? Where the new variables for the x and the argument for the x are equal to calling RCO on rho and xe. So this is going to look at the thing that xe is bound to. And when we see that, we're going to figure out what its new variables are and what the argument is. Then we're going to look at the new variables for the body, and the argument for the body are going to be RCO of sigma prime and the body expression, where sigma prime is equal to sigma, but there's a mapping from x to the argument for x. Now what this is going to do is it's going to say, if this xe right here is simple, meaning that it's another variable or a number, then we're going to completely remove it from the program. But if it's complicated, then this nvx is going to turn into a new let binding, and this ax is going to be that whatever that new variable is. So this is going to have the effect of doing renaming on variables. All right. So let's look at how this program really runs on an example. So let's move the screen back up. All right, there we go. All right, 310. So suppose that we have the following program. We're going to have an addition, where on the left is an addition, on the left of that is 2, on the right of that is 3. Then there's going to be a let that has an x and a read, and then inside there is a plus with an x and an x. Now let's label each one of these things. So we'll call this A, B, C, D, E. This is F, G, H, and I. Okay. So we're going to start off by calling RCO with an empty row, and we're going to give it the program A, which right here is this plus right here. All right. Well, that plus is going to call RCO on B with nothing. And that's another plus, so we're going to call RCO with nothing and C. And now here we can write an actual program. We're going to get back an empty list and a 2. We're also going to call RCO with an empty mapping and D, and that's going to be an empty list and 3. Okay. Well, that means that we're going to get a new variable up here, because we now know what RCOB is going to return. It's going to return a mapping that's going to say V0 is equal to plus of 2 and 3, and then V0. That's what RCO empty and B is going to call. Now let's look over here at E. Well, we're going to call RCO with an empty mapping and E, and that's a let. So it's going to call RCO empty mapping on F, and that's a read, so we'll know what it's going to return. It's going to return V1 and read, and then it's going to return v1 here. Well, now it's going to call RCO on G, but it's going to have a mapping that's going to say that X goes to V1. And we're going to call that on G. And that right there is a plus, so we're going to call RCO on the same thing and H, and that's an X right there. So we're going to get an empty list, and we're going to get V1. Then we're going to call it again on I, and we're going to get an empty list and a V1. And so those two things will determine what we get for G, which is going to be an empty, sorry, it's not an empty, it's going to say V2 and a plus of V1 and V1, and then V2. And then now we know that E has this for F and that for G, so we're going to combine them together. We're going to have the F first, which is going to say V1 goes to read. And then after that, we're going to have V2 goes to plus V1, V1. And then we're going to have V2 because that's the argument that got returned from the body G. Now these things will get combined up here into the top, which is going to have the definition of V0, which is going to be plus 2, 3. Close that. Then it's going to have the definitions of V1 and V2, V1 and V2. Then it's going to have a new one, which is going to be V3, which is going to be an addition of V0 and V3, sorry, V2. And then we're going to return V2. So altogether, when we serialize the program, it's going to end up being let V0 equal plus 2, 3, let V1 equals read, let V2, so that's V1, equals plus V1, V1, let V3 equal plus V0, V2, finally V3. Notice that that's exactly what I said we were going to output for this program, although I wrote an X right here rather than a V. Okay, so that's the RCO step. All right. Now, remember I told you that flatten is going to be a combination of RCO and this other one called explicate control. So let's write that down. So it's called econ, and it's going to take an R1 program that is in the RCO style, and it's going to return a C0 program. And it's extremely simple. You call econ on a program with some info and some expression, and what it does is it returns a program with that same information, and where main goes to T, where T is calling econ E on the E, and econ E on an argument is going to equal a return of that argument, and econ of a let x equals xe in be is going to be a sequence of setting x equal to xe and then doing econ e of be. And that's all we need to do. Everything else is just exactly the same. So at this point, you can implement the Uniquify pass. You can implement resolve complex. You can implement explicate control. That's what econ stands for. Explicate control. And for all of these, you can test that your interpreter does exactly the same thing on all of them. So what we'll do next time is we'll continue along the path of transforming C into the X language, and see you then.